Welcome back. We're talking about model selection and model complexity and how to choose an appropriate level of complexity. And now I want to give you a nice way to think about this in terms of the bias-variance decomposition. The bias-variance trade-off, as they say. So remember the bias-variance decomposition, when we were, and now this only, strictly speaking, this only applies when we're using the square loss, or sometimes people call it the quadratic loss. But it's a useful way to think about it, even in more general context. It's a useful analogy. So the bias-variance decomposition says that for an estimator, the mean squared error of the estimator equals the bias squared plus the variance. And let's think about what this looks like. Let's draw this sort of notional diagram here, where we have model complexity, the complexity of the parameters that we chose for our model. And let's say if it's, this is just sort of notional. There's no units or anything on this graph. But if model complexity is going along this axis, then what's going to happen is that if we draw the variance when we have large model complexity, your variance is going to be large. So this is the variance. And when you have low model complexity, the variance is going to be small. And likewise, when you have large model complexity, you're going to have low bias. Try something like this. And when you have small model complexity, you're going to have high bias, or high bias squared. Let's get rid of this so this isn't confusing. So why is this the case? Let's think just intuitively, let's think about this example here with regression. And let's pick a point. Let's pick a point like, let's say here, maybe this is a good point. Maybe that'll be a good example. So let's say that this is x here. This is some x that we want to predict the value for. And let's consider the estimator. Let's call theta. Let's suppose that this data comes from there is some true distribution from which this data was sampled. And let me draw a curve. Let's say that there's some true curve, something like this. And let's suppose that our data, maybe x is like, maybe x is uniformly drawn. You draw x uniformly from this range or something. And then you draw y to be normally distributed with some variance about this blue curve, this true blue curve. So this is the true. So blue is true curve. And so we could draw successive samples of the data by drawing randomly some x's and then drawing y's sort of normally distributed about this curve. And with data, with that sort of random model for our data, the estimator, so if we think about the maximum likelihood, there would be an estimator. The estimator for this point here, let's call this x. So the estimator would be the function that you get, so maybe like theta hat. It's a function of the data, and the data is random. So this thing is an estimator for the value of the curve. We're trying to estimate the true value. Estimator for theta equals, let's call it not f, let's call it, let's call it t for true. T is the true value. T of x is the true value. Theta is the true value at this point. And our estimator depends on the data. It's random. So our estimator has some bias and some variance. The expected value, so let's think about the case of b equals 1. That was this nice simple sort of case here with the line. And if we drew successive samples from our data and we took the maximum likelihood estimate under this class of for that particular model, that model would be when b equals 1. Then maybe we get some other data. We get a line like that, and then we get a line like that, and we get a line like that. We get some lines. And if we were to draw the distribution, for each of those, it went through went through a point here at x. It had some particular value at x. So if I drew the distribution of those, it would be maybe something like this, something like that. And that has a particular expected value. Maybe it's there. And so it has a bias. The bias is the difference between the expected value of the estimator and the true value of the parameter. In this case, the parameter is t of x, this thing. So that is the bias, right? That is the bias. And it's pretty big. It's not that great. It's not that great, but for this line, because the line is not really representing the data well. So when b was small, this had high bias. So that was here. So we had small model complexity, b was small. And we had pretty big bias, well, bias squared, I guess, to be precise, because to keep it non-negative and all. So bias squared was large. And now let's think about the variance. When b was 1, the variance is not too bad, right? When we got all these these different lines, it's not too crazy, right? They're all sort of centered around here. So the variance was small when the model complexity was small. Now let's think about big model complexity. Let's think about when b was 20. And let's think about if we got different samples from our data and we took the maximum likelihood estimate for w for that model, for the model with b equals 20. Well, what are we going to get? We're going to get all kinds of other crazy curves, right? Maybe we get one like that, and so the value, so for this one, we had a value down here from our original sample, and this one's way up here. It's crazy. So let me erase that and draw another one. Let's say we got some other thing, and maybe it's going to be like this. And so it's here, so it's maybe not too awfully crazy. And then we get a third, and maybe that one just goes way too low or something, down here or something. So you can see, I think you can see, that the distribution of the value, now if we took, right, the value, so this estimator is a random variable, and this estimator when b is equals 20 is going to have some if we drew samples from it, it's going to be some huge, wide distribution, something like this. It has a very high variance. This estimator has very high variance. So when the model complexity is large, we have high variance. When b is 20. And what about the bias? Is the bias low? The bias will be low because, well, it may be not completely obvious to see, but since this model can fit the data very well, then on average, since the data is going to be sort of centered around this, then on average, even though these curves are crazy, on average they're going to be about the right value. If you average them all up, if you took all those curves and you took the average of this point, of the value of your estimated curve at this value of x, and you average all those, then it's going to be about the right thing. So the bias is going to be low. And in order to to minimize your mean squared error, you want to find some appropriate trade-off. I drew these curves sort of suggestively, sort of convex like this. Sort of, I mean, oftentimes, because oftentimes what ends up happening is that the sum of these has this sort of shape. It has this sort of, this sort of shape where there's an optimal, maybe I drew that a little bit. It doesn't necessarily occur where these coincide. Could be something like this. So maybe the optimal point's like there. But the point is that you need to choose the appropriate level of model complexity for your class of models. And that involves finding an appropriate balance between the bias and the variance. So I hope that all made sense to you, and I think this is a nice, the regression example is always a nice one to come back to understand these concepts. And let me say one other point on this is that here we were talking about this estimator for a single x, right? But you could also think about this if you integrate, you can also define, if you were to integrate the mean squared error over the range of x's, if it was this finite range here sort of, then you could integrate your mean squared error and you would get a similar decomposition. Obviously, the integral would just be, it's linear. So you would get a similar sort of decomposition. And that you could think about your bias, your integrated bias and your integrated variance, your integrated bias squared and your integrated variance for the whole, thinking about your estimator now as being the whole function. All right, so I hope that was clear to you, and I think this is a nice way, even though it's particular. I'll make the disclaimer again. It's particular to the case of square loss. Square loss. It only applies, strictly speaking, when you're talking about square loss, but it's a nice analogy to think about even in other contexts as well.